Welcome back. This is another exciting episode of Mr. Takeda Teaches Algebra. I'm your host, Mr. Takeda, and I am going to teach you some algebra. This is lesson 4.5 from the Big Ideas textbook on analyzing lines of best fit, in which we ask the essential question, how can you analytically find a line of best fit for a scatter plot? Um, Previously, we put in a line of best fit, just kind of eyeballed it in, and we kind of looked at the distance from the scatter plot points to the line and determined that was a good point. But now we're going to kind of use our technology and talk a little bit more deeply about what's happening there. So the first thing we want to do is talk about the idea of residuals. Okay, here's the definition right here. And the residual, okay, so we have two data points on this diagram here, two data points right here and right here. Those would be like from the scatter plot. We put in a line of best fit. The distance, the y distance, the vertical distance from the line that we say is the best fit to the actual point, we call that the residual. Now that's why we said that we want the same number of points approximately above the line and below the line, and basically kind of like the same distances if we could. Okay, so how well it fits the line is going to how well the line fits the data is shown by the residuals. And what we'll do is we'll create a scatter plot of the residuals around the horizontal axis. If it's kind of like a straight line around the axis, it's a pretty good fit. And if it's kind of all over the place, then it's not going to be a good fit, a good correlation. Okay, and we'll talk about that word a little bit more in a second. So make sure you get the vocabulary word here down of residuals. You might want to draw the diagram just to kind of show yourselves what the residuals are. And let's look at an example here. This example was used on the previous lesson, and this table we've seen before, and it says the weekly sales of the DVD and the number of weeks since its release are shown in the table. And then here's the equation we came up with, y equals negative 2x plus 20. But we want to know, is it a good fit? So what we're going to do is go back to our friend Desmos and recreate this data table there. So I'm going to add an item, put it in the table, and then add 8 x values. For my y values, I'm going to put in 19, 15, 13, 11, 10, 8, 7, and 5. Okay, so here we have our scatter plot. So what we're going to do here is we're going to, in order to have the calculator do this work for us, since look what happened here. It labeled these points x sub 1 and y sub 1. So what we're going to do is, since we want to compare to this data, I'm going to say y sub 1. Now instead of equal, I'm going to use the little tilde, the little squiggly line, the top shifted top left key of your keyboard, tilde. And then I'm going to put in the rest of the relationship here. Negative 2x plus, 2x sub 1, just put the 1 in, plus 20. Okay, so now there's our line. There's our line. Now down here where it says residuals, go ahead and say plot. Okay, and now what it's doing here is giving us the difference between the y value from our scatter plot and the y value from our line. So x sub 1, here's 1, and we're saying that it's 19, but our line is 18. So we have a difference of 1, positive 1. This point is 1 above the line. Then at 2, we've got 15, but our line says it should be 16, so we're 1 below that line. Here at 3, our line says 14, but our data says 13, so a negative 1. So this is a -1, a -1, a -1. You see those things here. Let me use my pen. In +1 here, +1. -1, -1, -1. So that's what we have here. The next 2 points are on the line, so we have 0 as our residual. And the next 2 are above +1, +1. Okay, so that's what the residuals look like. When we plot it, see they're kind of grouping around the horizontal line like it's the graph line, above the line, below the line, below, 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 but above, below. So they're kind of following a straight line. It's kind of grouped around the x-axis. So this is a pretty good fit here. And again, we want to be able to use our graphing calculator to tell us these things. So this is a good fit. Let's go ahead and set up another. I'm going to clear this off of here, and we'll set up another one. Okay, so I've put in another data table here, and this is supposed to be a comparison of age. Our x value is someone's age, and the y value is their salary in thousands of dollars. So, for example, in the first set of data here, someone's 35 making $42,000. Someone's 37 making $44,000, etc. And we want to know whether the equation 0.2x plus 38 models the data. Okay, so let's find these data points here, first of all. Here we go. Turn that up so you can see that a little bit better. And again, so I'm going to say y sub 1 tilde, or squiggle, if you want to call it that, 0.2x sub 1 plus 38. Okay, now, so first of all, we can see the data that has been plotted is not really a straight line. And we're trying to use a straight line here to model this. So that's not working out very well. So let's go ahead and pull back out here a little bit so we can see the x-axis. I'm going to click plot. And you can see that this is more of a U shape. So this is not going to be a good model for this data. You can see our residuals here, -3. Some go pretty high, like 5, 3.6, 3.4. Those are way above the line. There's a few that are below the line, the negative ones here, but they're not nearly as big as the positives. So this is not going to be a good model for our data. Okay, so the next thing I've done here, right, I put a table in here, and this table shows the duration, x, in minutes, of several eruptions of the Old Faithful geyser and the times, y, in minutes until the next eruption. So we want to use the calculator now to find the line of best fit. So here's what we're going to do. Okay, so there's, from our scatter plot, we're going to do now to come up with a line of best fit, have the calculator do that for us, is similar to what we did last time. So down here at 2, I'm putting y sub 1, squiggle, but now instead of putting in the values for slope and y-intercept, I'm going to use m and b. So m times x sub 1 plus b. Now here's my line. This is the line that the calculator came up with. So it's telling me that my m is 11.99 and my y-intercept is 35.107. So what I have here is m, I'm sorry, let me say y equals 11.99 times x plus 35.107. But if you notice that if you said 12x plus 35, you'd probably be pretty close. I'm going to plot the residuals here so I can see what those look like. So again, those kind of form a straight line around the x-axis. Kind of the same pattern you see here, but around the x-axis. Here you see our residuals. And down here, this R, 9.79. This is the correlation coefficient. The closer this is to 1, the better your line of best fit is. If it's close to 0, then it's not a real good correlation. So this one, because the calculator came up with it, this is the best possible, and it's a 0.979. So this is a really strongly correlated line of best fit for this data. One thing I want to mention here is the slope and y-intercept. The slope in this case is 12, 11.99 or 12, and this means that the time until the next eruption increases by 12 minutes for each minute the duration increases. Let me say that one more time. This means the time until the next eruption increases by about 12 minutes for each minute the duration increases. The duration of the eruption itself. Okay, but the y-intercept has no meaning here because this idea of 0 minutes really doesn't have any meaning in this context. Let's take a look at the next thing we're going to look at is interpolating and extrapolating data. So looking at interpolating and extrapolating data, interpolating means you don't have data, specific data on something, but you're going to try and figure it out using data points that you have. And essentially using 2 data points you have, you're going to be between those data points. So this is interpolating because you're between data points. Extrapolating means you're going to try and predict something past the data that you have. So in the last example, we came up with this equation. I'm going to use the more approximate y equals 12x plus 35. And we want to know what's the approximate duration before a time of 77 minutes. So we're going to put in 77 equals 12x plus 35. Subtracting 35 from both sides. 7 minus 5 is 2. 7 minus 3 is 4. Equals 12x. So x is going to be 3.5. Okay, so we have a new data point, 3.5 and 77. Next, we want to say predict the time after an eruption lasting 5 minutes. Okay, so we have an eruption that goes 5 minutes. How long? We want to predict the time after that 5-minute eruption for the next eruption. Let's go back here. Here's one neat thing we can do here since we have our line of best fit. Here we've got all these data points here, 3.7, 4.2, etc., 4.4. Here's my scale in minutes. Here's 5 minutes. I go back up here. I can just click on this point, hold it there. So at 5 minutes, 95 minutes here, 95.06, so approximately 95 minutes for after 5 minutes. That's interpolation, extrapolation. Let's go back and look at one more thing here. We want to look at correlation and causation, and this is just an explanation of these words here. It says, tell whether correlation is likely in this situation. If so, tell whether there's a causal relationship. Causal relationship means something causes something else to happen. So, letter A, time spent exercising and the number of calories burned. Well, we can logically reason that the more time you exercise, the more calories you're going to burn. That they go hand in hand. One causes the other. What causes calories to be burned? Well, the amount of activity you have. So the more time you spend exercising, the more calories you're going to burn. There's a causal relationship there. There's of course a correlation there, because calories burned, more calories burned, meaning more time spent exercising does mean more calories burned. They go hand in hand, but one causes the other. Now, if we look at B, the number of banks and the population of a city, well, generally, the bigger the city in terms of the number of people that live there, the more banks you're going to have, right? But the number of banks does not cause the population of a city to grow. So you could have a city and build, 10 extra banks. That's not going to automatically raise the population of the city. the number of banks does not cause the population of the city to grow. So there's no causal relationship there, even though generally the greater number of banks in a city, the greater the population of the city, but one does not cause the other. Okay, so that's correlation and causation. Just a couple of extra words for you to think about there, and that's it for now. The scout says, I'll see you in class, and be safe out there, my friends.